This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and the scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form AB, Question 2. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Form AB Question 2 involves a particle moving along the y-axis. Its position is modeled by a twice differentiable function y of t, where t is measured in seconds and y of t is measured in meters. We're given a table of values of y prime of t for selected values of t, and we also know the position of the particle at time t equals 12 is minus 3. In part C, we need to explain the meaning of y double prime of 4 in the context of the problem, and use correct units in doing so. I think the important idea here is to determine the units attached to a derivative. And as an aside, over the past 5 to 10 years, these kinds of questions, where units are important, have appeared more frequently on the free response portion of the AP Calculus exam. Now, I think it's easier to determine the units associated with a derivative if we use Leibniz notation. And it's pretty straightforward. For a derivative represented by dy dx, the units are simply the units of y divided by the units of x. Here's a quick example. Suppose y is a function of x, and y is measured in miles, and x is measured in hours. Then the units for dy dx are miles divided by hours, or, more commonly, miles per hour. And suppose we go just a little bit farther and consider the second derivative. That is, the second derivative of y with respect to x twice, or d squared y over dx squared. We can think of this expression as the derivative of y prime over dx. So the units are the units associated with y prime divided by the units associated with x. So in my example, this would be miles per hour divided by hour, or miles per hour, or maybe more commonly, miles per hour squared. Let's use this method of finding units, plus a few additional definitions, to solve our problem. We know that y is measured in meters and t is measured in seconds. So y prime of t, which is dy dt in Leibniz notation, has the units meters divided by seconds, or meters per second. This is the velocity of the particle by definition. Velocity is defined to be the change in position over time. The second derivative is the derivative of y prime over dt. So the units are meters per second divided by second, or meters per second squared. And this is the acceleration of the particle, by definition, the change in velocity over time. So finally, to answer our specific question, y double prime of 4 is the acceleration of the particle in meters per second at time t equal 4 seconds. Here are the scoring guidelines for this question. Pretty straightforward. 1 point for the correct meaning with units. And by meaning, we want the student to recognize that the second derivative is the acceleration of the particle, and the student must also refer to the specific time, t equal 4. Here are some interpretations of these guidelines to help award points and to prepare for problems like this on the next AP Calculus exam. This question seems pretty simple, but there are a lot of little things that a student must convey correctly in order to earn this point. First, here are some responses that earn the point. Notice that all three of these responses refer to the acceleration, have the correct units, meters per second squared, and they also refer to the specific time, t=4. Here are some common student responses that do not earn the point. Y double prime of 4 is not the rate of change of speed. Remember that speed is the absolute value of the velocity. And the reference to the particle speeding up is not correct either. Just a few additional comments about the scoring here. The units presented by the student must include meters per second squared. However, the student does not have to present the units for t=4. But if they do, they must be correct, that is, in seconds. Even if the student had presented correct units in parts A or B of this free response question, if they present incorrect units here in part C, they do not earn the point. And finally, if the student presents x=4 seconds instead of t=4 seconds, they are still eligible to earn this point. In part D, we need to find the average value of the acceleration of the particle over the time interval 0 to 12. One of the key concepts needed here is, of course, the definition of the average value of a function. Now, I think this is a very nice application of the definite integral, because we can visualize this concept, and we can derive this result using our typical method for deriving many calculus concepts. That is, we approximate the result with a finite number of terms, and then consider what happens as n goes to infinity. So let's suppose we have a finite set of numbers or observations or values. It's straightforward and common to find the average, or really the arithmetic mean, of this set of numbers. All we do is add them all up and divide by the total number of values, n. But how do you compute the average temperature during a day, for example? There are infinitely many temperature readings during the day, and we can't find the average in the usual finite way. But if you think about it, it certainly seems like there is an average temperature during a day. This graph shows an example of a temperature function, capital T, given in degrees Fahrenheit. And it also shows a guess at the average temperature during the day. It seems like the value is sort of in the middle of the temperature function over the interval 0 to 24. But how do we find this value? So let's try to compute the average value of a function y=f of x over the interval a to b. We'll start by constructing a regular partition of the interval a to b. And that is, we'll divide the interval a to b into n equal subintervals, each of with delta x, which is b minus a, divided by n. Now, select values x sub I star in the ith subinterval, and then compute the average of the numbers f of x sub 1 star, f of x sub 2 star, all the way down the line to f of x sub n star. So add them up and divide by n. In my temperature example, if n equals 24, then we would take temperature readings maybe every hour and then find the average. Seems like a reasonable approximation to the average value of the temperature function over a day. Since delta x is equal to b minus a over n, we can solve for n in this expression, which is b minus a divided by delta x. Now, use this expression for n to rewrite the average value. A little simplification, and an approximation to the average value of the function, written using summation notation, is this expression. 1 over b minus a times the sum from I equal 1 to n of f of x sub I star times delta x. As n increases, the expression is the average value of a very large number of values. In my temperature example, as n increases, we might be averaging temperature readings taking every minute or maybe even every second. And it seems reasonable that if we want a better and better approximation to the average value of a function, we should let n get bigger and bigger, or increase without bound. This summation that we arrived at is a Riemann sum, and the limiting value is the definition of a definite integral. So the limit as n goes to infinity of this sum is this definite integral. Therefore, we define the average value of f on the interval a to b as 1 divided by b minus a times the definite integral from a to b of f of x dx. And here is a special application of the average value. If f is a non-negative function on the interval a to b, then the average value can be interpreted as the average height of the graph of f, and it's equal to the area under the graph of f from a to b divided by the width of the interval. It's pretty easy to sketch an example of this application to help justify this interpretation. Now, we'll also need to use the Fundamental Theorem of Calculus, traditionally called Part 2, to solve this problem. The FTC is discussed in detail in other videos. Let me just say here that the FTC Part 2 provides a much simpler method, instead of considering the limit of a Riemann sum, for the evaluation of definite integrals. The theorem says that the value of the definite integral from a to b of f of x dx can be obtained by finding any antiderivative, capital F, of the integrand, little f. And then we subtract in the proper order, capital F of b minus capital F of a. Let's put these ideas together to solve this problem. The average value of the function y double prime over the interval 0 to 12 is, by definition, 1 divided by 12 minus 0 times the definite integral from 0 to 12 of y double prime of t dt. We do not have a symbolic or analytic expression for y double prime of t. However, we do know that y prime of t is an antiderivative. So by the Fundamental Theorem of Calculus, the definite integral is equal to y prime of 12 minus y prime of 0. We can find these values in the table that was given in the statement of the problem. And a little simplification leaves us with an answer of minus 3/4. Here are the scoring guidelines for this problem. Part D is worth 3 points. 1 point for writing the correct definite integral as part of the definition of the average value of a function. 1 point for using the Fundamental Theorem of Calculus correctly, and 1 point for the final answer. Here are some interpretations of these guidelines to help award points and to prepare for problems like this on the next AP Calculus exam. The first point, the integral point, is really a definite integral point. This point is earned for the integral expression with the correct integrand and the correct limits. The student must be trying to find the average value of y double prime. In other words, if they have a correct average value expression for another function, like y prime or even y, they do not earn this point. The constant in front, 1/12, is associated with the third point, or the answer point. The second point, the Fundamental Theorem of Calculus point, is earned for the expression y prime of 12 minus y prime of 0. We really need to see this expression, or rather sufficient evidence of this expression, for the student to earn this point. And the third point is earned for the correct answer only. The values of minus 5 and 4 must be shown by the student. And here's a minimal student response that would earn 2 points. They do not earn the integral point, but there is just enough evidence of the Fundamental Theorem of Calculus, and the final numerical answer does not need to be simplified. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts, and a reasonable expectation of how they would be scored. We'll look at more parts of this free response question in the next video.